Today we're diving into a really provocative idea, the end of logging. I know, that's a huge claim, right? But we're going to explore how a massive shift in software is letting our apps do more than just tell us they failed. It's letting them predict their own failures before they even happen. Let's get into it. So let's just get right to the heart of it. If you're an engineer, you know this pain all too well. Why is finding the root cause of some problem in a modern app so ridiculously hard? It's not just like finding a needle in a haystack anymore. It's more like finding a needle in a haystack that's inside another haystack. And to really get why this is happening, we've got to look at how our old tools, the ones we've trusted for years, are starting to fail us. Why traditional monitoring just isn't cutting it anymore.
For like forever in tech years, we've relied on this playbook called the 3 pillars of monitoring. You had your logs, specific time-stamped events. You had metrics, things like CPU usage, which are basically just numbers over time. And then you had traces, which tried to follow one single request as it moved through your system. And look, for a long time, that worked. It was totally fine.
So what changed? Well, pretty much everything about how we build software today. We went from these big, beautiful monoliths where everything ran on one server and you could just grep a log file to find your answer, to this new world of microservices. And now, instead of one app, you have hundreds of tiny, independent services all trying to talk to each other.
And here's where it gets real. Just think about an e-commerce site. That one little click on the checkout button, boom, that can kick off a chain reaction across dozens of different services. Payments, inventory, shipping, fraud detection, you name it. And every single one of them is spitting out its own data, completely shattering the story of that one click into 100 little pieces. And that, right there, leads us to the next massive headache. It's not just about the complexity. It's the unbelievable, unimaginable amount of data that this complexity creates. We are literally drowning in it. This absolute fire hose of telemetry data from all those services gives us a punishingly low signal-to-noise ratio. Somewhere in that ocean of data is the one thing that actually matters, but good luck finding it. You have all the data in the world, but somehow 0 actual answers. What this really means is that the kind of problems we're fighting has totally changed. We've gone from dealing with known unknowns, predictable issues with a clear playbook, like CPU is high, so I'll check the process list, to fighting unknown unknowns. These are just weird, ghostly failures that pop up out of nowhere from the interactions between all these systems. They're problems you never even thought to look for. An unknown unknown isn't a server just falling over. No. It's this absolute nightmare scenario. Imagine getting a bug report like this. How on earth are you supposed to debug that with your old tools? You can't. It's pretty much impossible. Okay, so we've painted a pretty bleak picture, I know. But here's where the story takes a turn for the better. Because out of all this chaos, a new standard emerged that acts like a universal language, allowing all these different services to finally speak to each other in a way that makes sense. And that language is called OpenTelemetry, or OTel for short. Now, this isn't some tool you go out and buy. It's a universal standard, backed by the CNCF. Honestly, you should think of it as being as fundamental as TCP/IP is for networking or as SQL is for databases. It's that big of a deal. It's one common way for every service to report what it's doing. So, how does OTel magically fix that shattered story problem? It all comes down to its killer feature, context propagation. When a request first hits your system, it gets a unique trace ID. Then, that ID gets passed along in the headers to every single service that touches the request. It's literally like putting a FedEx tracking number on the request, allowing us to stitch all those scattered events back into one single, coherent story. And the impact of this was just massive. It completely turned the industry on its head. OpenTel basically made the act of collecting data a commodity, a solved problem. Suddenly, observability companies couldn't just compete on who had the best agent anymore. The whole game changed. Now, the battleground is all about who can provide the smartest analysis and the deepest insights from that standardized data. So now we have all this amazing, unified data. But to really unlock its power, we have to completely change how we think about what a trace even is. We have to look at it differently. See, most of us think of a trace as just a timeline, right? A simple chronological list of events. But that view is fundamentally incomplete. It's so much more than that. A distributed trace is actually a directed acyclic graph, or a DAG. I know, that sounds super nerdy, but stick with me, because this one little shift in perspective changes everything. When you see the trace as a graph, it all just clicks. Each operation or span is a node in the graph. The calls between them, those are the edges, the connections. And now, all of a sudden, you can apply decades of graph theory to your debugging. You can instantly find the critical path, which is just a fancy way of saying you can see in a split second the exact sequence of events that's causing the slowdown. But, of course, there's a catch. A modern system can generate trillions of these events every day. You can't store all of that. It would be ridiculously expensive. So you have to be smart about what you keep. You have to sample your data. And really, there are two main ways to do this. First, you've got head-based sampling. This is where you decide to keep or drop a trace right at the very beginning. It's cheap and easy, but it has a huge blind spot. What if an error happens later on in the request? Oops, you already threw the evidence away. The smarter way is tail-based sampling. It waits until the entire trace is finished, and then it looks at the whole story and decides if it's interesting enough to keep, maybe because it had an error or was really slow. It's way more powerful, but it's also a lot more complex and expensive to run. And that brings us to our final section, the real end game of this entire shift. We're moving beyond just watching our systems to actually, truly understanding them. Ultimately, the goal here is to make the leap from simple correlation to true causality. It's one thing to notice two things happen around the same time. It is a completely different universe to know for a fact that one thing caused the other. And this is what that difference looks like in the real world. You go from a vague guess, like, slow requests seem to be correlated with this log message, to a powerful, actionable insight. A 50 millisecond latency increase in the auth service is the probable root cause of the payment failure. Now that is an answer an engineer can actually do something with.
And what's the business impact of all this? It's this: a massive, dramatic reduction in mean time to resolution, or MTTR. This isn't just a cool tech demo. This is about finding and fixing production issues that impact your customers in minutes instead of hours or days. That has a huge effect on the bottom line.
And so that leaves us with one final thought to chew on. We've talked about how this whole new approach can tell us why our application failed. But what's the next frontier? What if, by analyzing all these causal relationships in real time, your application could tell you when it's about to fail? That's the future we're headed towards.